Very good morning to all the participants. So we are on the final day of our international webinar series on applications of mathematics. So the first 2 days were quite fruitful with lots of discussions, lots of interaction between the participants and the resource persons. So we expect the same to continue today also. So for today's session, we have Professor Kallol from Jadavpur University. Yeah. Kallol sir from Jadavpur University. He will be joining. Hello, sir. You are live.
Good morning. Yeah. Good morning.
Very good morning, and thank you very much for being with us for this seminar. I'm also adding our guest, Dr. Navakanto Sharma from Assam University, Silchar, and Dr. Uday Shankar Chakraborty from Assam University, Silchar. They are both my teachers. And I'm also adding Dr. Anirban Roy from Christ, deemed to be University, Bangalore. He's also there with us. Okay, and I'll ask one of my students to join also. Just I'm sending him the link. Okay, one of our students will also join the live stream. Okay. So for the participants, we'll be providing the feedback link just at the end of the lecture. And for today's session, we will also have a live feedback at the end of the lecture so that we can have an idea how the participants feel. We also have now, Dr. Swapan Malik from University of Oklahoma, USA. He has also joined us. Yeah. Oh, I think he will be visible to some time. Oh yeah, he is visible there. Right. Thank you, sir, for joining, Swapan sir. Okay. Let us just wait for Sumli. I'll just call her up.
Thank you very much.
Okay, yeah. Just I'll make a call to my student. Please wait for some time. Okay, I think she is having network problems. She just messaged me. Okay, so let us begin. She's not being able to join. Once again, I formally welcome our speaker for today, Professor Kallol from Jadavpur University. I'd also like to read out his biodata. Okay, so Professor Kallol is currently working as a professor in the Department of Mathematics, Jadavpur University, Kolkata. His area of specialization is in functional analysis, which is one of the most fundamental areas in mathematics. He completed his graduation from Gurucharan College, which was under Guwahati University in the year 1990, and stood first class first and best graduate, securing 84% in BSc examination. Though he completed, then he completed his post graduation from Jadavpur University in 1993, and there also he stood first class first and best postgraduate of the university in MSc examination. So later, he was awarded his PhD degree from the same university in the year 19. The year is. Sorry, I forgot the year. For his magnificent 1999. Yeah. Okay. I think I did wrongly. Thank you, sir, for his magnificent research work in functional analysis. Professor Kallol Pal is the supervisor of around 18 PhD students, out of which already 9 students have been awarded PhD under him, and 9 are still ongoing. So during this short period of time, he has achieved a lot. He was awarded INSA Bilateral Exchange Award for visiting University of Szeged, Hungary in 2019, sponsored by INSA and Hungarian Academy of Science. Moreover, he was awarded by SN Bandhu Memorial Gold Medal, DN Datta Memorial Gold Medal, and gold centered silver medal, and Dr. S.K. Banerjee Memorial Silver Medal for securing highest aggregate of marks in postgraduate in 1993. Also, Sir has organized many international conferences on analysis, algebra, combinatorics, and their applications. He handled a total of 12 projects and delivered lectures in 52 national and international conferences. He also headed as a referee in many national and international journals that includes publications from Springer, Taylor and Francis, Elsevier. He is highly skilled and has in-depth knowledge in functional analysis, and is also a very good researcher and a very good teacher. I have attended his lectures. So it's really an inspiration and an honor for us to have him with us. So without further delay, I'd like to request Kallol Pal sir to kindly begin his talk. So it's a 1-hour talk, and after that we'll take up questions from the participants as well. Sir, you can share your screen.
Yeah, thank you, Devashish, very much. Just guide me for a moment whether I'm doing it right or not. Yeah. Yes, thank you so much for your nice words. Let me see how much justice I can do to those words. Yeah. Is the screen sharing done? No.
Yeah, I'll get a notification here. I'll just check. Yeah, I got the notification.
Yeah, it's done now.
Screen is visible. Yeah, screen is visible.
So, is it okay?
Yeah, you can put it in presentation mode, slideshow mode.
Where it is?
I think it's in Command L or full screen view or presentation view.
Full screen view, no? Full screen mode, yeah.
Is
it okay?
Now it's okay. Yeah, and you can hide that pop-up message there. There's an option hide. Yeah. Now all the slides will. Yeah. It's I think. Yeah. Yeah.
Now it's. Okay.
Yeah, it's visible, sir.
Yeah.
So you can try changing one slide. I'll just check.
Yeah.
Yeah, it's okay.
Is it okay?
It's okay.
Fine. Yeah.
Yeah. So I'm going backstage now, sir. It's up to you.
Okay, surely. Just remind me if I am doing slow or late or something like that. Maybe I can communicate with you on all the time, I believe, right?
Yes, I'll be here itself. I'm just moving out of screen. All the other resource persons are also here, and guests are also here with us.
Okay.
So we can begin.
Yeah. Okay, fine.
So participants can see your presentation as well as your video. So both can be seen.
Yeah, fine. Okay. So once again, I thank Devashish for organizing this international webinar series, and special thanks to him for inviting me to deliver a talk in this series. I have a connection with Gurucharan College, as Devashish informed you all. So that's my actually native place. So where I was born and brought up. My more than 20 years of my life has actually been in Silchar, and that was the most important part of my life that I spent in Silchar. And after that, I moved to Kolkata, Jadavpur University, and from then onwards, I am in there only, right? Fine. So the topic that I have chosen to deliver a talk on is Hahn-Banach theorem, which is the actually the pillar, the fundamental theorem of function analysis. The function analysis actually build on that actually. So this is one of the most important, in fact, the most important theorem in function analysis is Hahn-Banach theorem. And talking of these two mathematicians, Hahn and Banach, I'll just talk a few words about them. Hahn is an Austrian mathematician and Banach is a Polish mathematician. And both of them more or less have done the same in almost same time. And their lifespan is also around same, I think 52, 53 years they have their lifespan. And but Hahn was, in this type of family where his father was doing job and all these things. Banach's father, on the other hand, was in military service, and Banach's mother was from a very poor financial background. And at that time, there was some regulations that the military, these servicemen cannot marry or something like that. So in a sense, Banach was never with his mother after his birth, actually. And this Banach surname is coming from his mother only, right? Stefan comes from his father, and Banach surname he has taken from his mother only. So Banach has he was being baptized later on, and then he was being taken care by some aunts and all these things like that. And maybe 2 years back, I visited Krakow, where Banach was actually born and brought up. So, and this is a nice place, and I have been lucky to visit his birthplace. And actually, my entire research area, I have been with this Banach space, and Banach space. So let us come to the main point now, Hahn-Banach theorem. So this theorem is known to all those students who are in post-graduation, I believe so, and maybe and then onwards. But undergraduate students may not have this term, familiar with this term, Hahn-Banach theorem. So for them, I will try to put it in a naive way. So how do I look at this Hahn-Banach theorem? So this is, and what are some of these connected results, and then these applications and all these things. So more or less the outline of this, my talk will be like this. So the geometrical motivation will definitely form the major part of this talk. Then we'll go to this very brief proof of Hahn-Banach theorem. Then we'll talk of this uniqueness of Hahn-Banach extension, then separation of convex sets, then what about Hahn-Banach extension for operators, and finally we'll talk of application of Hahn-Banach theorem, which we are recently doing in the study of geometry of Banach space through Birkhoff-James orthogonality. There are many areas where these applications are there, because I have already told you all that this Hahn-Banach theorem is the most important theorem in function analysis. There are 4 or 5 very important theorems in function analysis, and Hahn-Banach is one of them. The most, I rate it as the most important theorem of function analysis. So to begin with geometrical motivation, so let me begin with the following figures. So first, you can see there is a circle, and there is a line tangent to this circle, right? So this circle has a tangent line. So now you think of a sphere containing that circle, right? And obviously you can think of infinitely many planes containing this line, right? You can think of one sphere that contains this circle, and you can think of infinitely many planes containing that line. And out of those planes, there will be one plane which will be tangent to the sphere. So that is very much geometrical. So let me show it this way. Oh, sorry. Yeah, this one, right? So this is a circle. So this is a straight line. And so this is a sphere where the circle is a part of that sphere. And then you have this plane actually. So if you have a circle with a tangent line, then you can definitely have a sphere that contains the circle, and then this plane is actually touching the sphere at that particular point. Similarly, we can think of this also. There is a box square. So, and that is a point. So if you think of this as a point, then a corner point, then there is a line, right? Which is actually keeping the square on one side. I won't say it's a tangent line, but I will say this square box is on one side of this tangent line. So now containing this square, you can think of a cube or a box, and containing this line, you can think of infinitely many planes actually. So you can see there will be at least one plane which is containing the box on one side. So how does it look like geometrically? So you can see like this. So this is the square. So now you have this box. So you can see there is a plane that is actually keeping this box on one side of this. So I'll come to this later on. So this is actually going, so here having a square and having a line like this and going to box, having a plane like this, or having a circle and a tangent line and going to sphere and this is actually, this is one is Hahn-Banach extension actually. This is what is Hahn-Banach theorem. So I will explain it in details throughout this lecture, and hopefully you people will be able to get some flavor of this, how I'm connecting all these things. So now, for the sake of those who are familiar with Hahn-Banach theorem, so I will just state it, and then later on I will describe all the terminologies, right? So just for the time being, if someone is not familiar with Hahn-Banach theorem, he or she does not have to worry too much. Just see the statement, and then we'll go back to these connections, right? So my aim of this lecture in the initial part is to show that this is actually what is Hahn-Banach theorem. So this geometrical from square to cube line on one side, then plane on another side, this is what is Hahn-Banach theorem all about. So the statement of Hahn-Banach theorem is very simple. If you have a non-linear space and you have a subspace where there is a bounded linear functional, then you can extend it to the whole space. So f is a bounded linear functional on a subspace M of x, then there exists a bounded linear functional G such that G restricted to M is equal to f, and norm of G is equal to norm of f. So this is what is called non-preserving extension. So if you have a Banach space or a nonlinear set, and you have a subspace where there is a bounded linear functional, you can extend that bounded linear functional to the whole space without disturbing the norm, actually, keeping the same norm. So this is what is Hahn-Banach theorem. So I will show that those two figures are really connected with this. So for that, we'll go very slow initially, just to keeping in mind those students who are here listening to this lecture, right? So first, let me begin with what is a linear functional on a vector space. So on a vector space, linear functional is something like this, that is additive and homogeneous. So f of alpha x plus y equal to alpha fx plus y. So if you take alpha equal to 1, that is f of x plus y equal to fx plus y. And if you take y equal to 0, then f of alpha x equal to alpha fx. So this is what is linearity and homogeneity all about. So the advantage of a linear functional on a vector space is that actually you can define the mapping on the basis, and then you can extend it to the whole space. I'll come to that later. And corresponding to each functional, there is a kernel. Kernel is the collection of all those vectors which actually taking images to the 0. So set of all x such that fx is equal to 0, and we all know that this kernel is a actually subspace of the vector space X. So right now I am not talking of any norm. So I am purely on an algebraic structure. So there is a vector space, there is a linear functional. First I will see how can I connect this functional geometrically with some objects, right? So that is what is first ambition, or my aim is that. And then we'll see how can we connect continuous linear functionals in a norm space with some geometric objects, right? So for there is a definition of hyperspace also. Hyperspace is nothing but one dimension short. So let X be a vector space, okay, then a subspace H of X is said to be an hyperspace if codimension of H is 1. That is if X is equal to H direct sum H for some non-zero X. A hyperspace is a maximal proper subspace of X. So if you are in R3, so this plane passing through origin are your hyperspaces. If you are in R2, then your straight line passing through origin are hyperspaces. So one dimension short. So if you are in R to the power n, then all those R to the power n minus one dimensional subspaces are actually your hyperspaces. So one dimension just short. And translation of an hyperspace is called a hyperplane. So just you translate it. So if you have a hyperspace H, then X plus H is actually your hyperplane. Fine. So now how can you see a linear function, a non-zero linear function in a vector space? So then that's a very easy theorem. That's f be a non-zero linear function in a vector space. Then codimension of kernel of f is 1, and f is determined by kernel f and any value of f at an element not in kernel f. So that's a very easy theorem. That's a very standard textbook theorem. Although I've written the proof for here, so when I share the slide with you all, you can have a look at this. So basically it says that if you have a non-zero linear function L, then you can decompose this space X, direct sum decomposition, that will be kernel F plus some vector for which image is not equal to 0. That is what actually we are doing here. X is equal to kernel F, direct sum of span of X. That is what I proved here, right? So any element, so once this X is equal to kernel F, direct sum span of X, then any element you can write it as actually alpha X plus Y, where alpha is a scalar and Y is coming from kernel F. So whenever you have a non-zero linear function L, right, then kernel F is a subspace, and the original space get decomposed into kernel F plus span of some element, where the image of that element is actually non-zero. Now we move to the next slide. So if there are two linear function L for which kernel of F equal to kernel of G, then then this F and G are actually linearly dependent. F equal to lambda G for some lambda belonging to K. So basically what happens whenever kernel F equal to kernel G, and as already we have seen this, F is determined by the kernel F as well as some value where function is non-zero. So if you take that some value where F is non-zero, so for example, if you take X such that Gx is not equal to 0, then Fx will also be not equal to 0 because kernel F equal to kernel G. So you know Gx and Fx are scalars, so there will be some lambda such that Fx equal to lambda into Gx. So what does actually matter in case of non-zero linear functionals? Actually, kernel, if you have the kernel same, then outside kernel there will be multiple. There is no doubt regarding that because they are all scalars. Fx will be some lambda into Gx. Two non-zero scalars, you will get another non-zero scalar lambda for each Fx equal to lambda into Gx. So now you can see since they are equivalent kernel of F and kernel of G, so they will be forced to be equal for all elements. Then F will be equal to lambda into G. So let us move a little further. So what is the connection between non-zero linear functional and hyperspaces? That's the most important thing. Given a non-zero linear functional F, there exists a unique hyperspace. Given a non-zero linear functional F, there exists a unique hyperspace. On the other hand, given a hyperspace H, there exists a non-zero linear functional F such that kernel of F equal to H, and the functional F is unique up to linear independence. So there may be more than one F. So if you have another G for which kernel G equal to H, then you know by the previous theorem, then F will be equal to lambda G. So this connection is most important. So given a non-zero linear functional on a vector space, so I can see geometrically it is a hyperspace. And given a hyperspace, I can find a non-zero linear functional such that kernel of F equal to H. The proof is here given, but I go to the figure, geometrical part. I think there is a figure after that. So that's an example. Yeah, that's an example. So F, I have taken a linear functional which is taking 1, 0, 0 equal to 2, 0, 1, 0, 3, then 0, 0, 1 equal to 3. Then for any F, x, y, z, f, x, y, z equal to 2x plus 3y plus 4z. So if the linear functional is f, x, y, z equal to 2x plus 3y plus 4z, so the corresponding hyperspace is actually 2x plus 3y plus 4z equal to 0. So F corresponds to this hyperspace. Conversely, if you take any hyperspace x, y, z equal to x plus y plus equal to 0, then you can easily see this H is corresponding to this linear functional F. Not only this, and you can actually, this hyperspace will correspond to any G for which G is some multiple of F. So that will look like A into x plus y plus z for any not equal to 0. So this is what is actually geometrically. Where is my figure? Yeah, that's my figure. So the figure is somehow misplaced. So this is your hyperspace. So if the linear function is f of x, y, z equal to x plus y plus z, so the hyperspace that is connected to this linear functional is actually x plus y plus z is equal to 0. So now, so in a vector space, non-zero linear functionals and hyperspaces are actually connected. So given a non-zero linear functional, I can visualize it as a hyperspace, and given a hyperspace, I can find a non-zero linear functional which is associated to it like this. So now we want to come to this norm-linear space. So what happens if the linear functionals are in a norm-linear space? So in a norm-linear space, what happens? So for that, I'll just briefly describe about this norm. So what is the definition of a norm? So norm is something like this. So every norm x, there is a function from, sorry, it's miswritten. It should be x to r. Yeah, it is typo. So there is a function from x to r for which norm x is greater than equal to 0, norm x equal to 0, if and only if x equal to 0, this norm of x equal to mod a into norm x for all a belonging to k, and norm of x plus y is less than equal to norm x plus norm y, right? A vector space with a norm defined on it is called a norm-linear space. So norm is a function. I again say that this should not be there. So this is a function from x to r satisfying all these 4 conditions. The most important inequality is this, the triangle inequality in a norm-linear space, which actually ensure that some convexity property on the space. So just a few words about this norm. And norm on x defines a metric D by this. So every norm-linear space is a metric space. However, not every metric space is a norm-linear space. The two most important notions connected with this norm is Sx, which is your unit sphere, and Bx, which is unit ball. So Sx is the collection of all x for which norm x equal to 1, and Bx is the collection of all x for which norm x is less than equal to 1. These are the unit sphere and unit ball of the non-linear space. So now I go back to this connections. My aim is to explore the connection between linear functionals and hyperspaces in a non-linear space. So first, I observe that a hyperspace in a non-linear space is either closed or dense. There is no other option, and that's very not so difficult to see, because hyperspace means there is only one dimension less. So if I have given a proof here, let me describe something, an alternative approach to this proof. So if you have a subspace, closed subspace H, whose codimension is 1. If you have a subspace H, whose codimension is 1. Suppose H is a subspace whose codimension is 1. Now, closure of a subspace is again a subspace. So you look at this H closure. Now what can happen to H closure? H closure can be either equal to H and it can go to X, because codimension is 1. So H closure is either equal to H, and if it goes to higher dimension, then it should be equal to X. So whenever H closure is equal to H, then it is a closed hyperspace, and whenever H closure is equal to X, then it becomes a dense hyperspace. So any hyperspace in a nonlinear space is either closed or dense. So I have given an example of a dense subspace here out. So I will talk of this dense hyperspace later on. So if you just look at this C0, or a collection of all sequences x tending to 0, and C00, x is equal to C0 and y equal to C00. That means all sequences in C0 for which all but finitely many xn are non-zero. Then it is not very difficult to see that this C00 or y is dense in x, and that's a very simple proof what I have described here, right? So when I will share the slide with you, you can see how this proof is going on. So that's very not so difficult. So we have an example of a dense subspace, right? So there are dense subspaces and there are dense hyperspaces also. I will see just a few slides later on, right? So hyperspaces are, so I have to remember that hyperspaces are either closed or dense. There is no other option in a nonlinear space. Now, the continuous linear function, that's the most important thing. Continuous linear functionals will always correspond to closed hyperspace, and closed hyperspace will be corresponding to continuous linear functional. So that is the crux of the matter. So if you have a non-zero linear functional f, then kernel f is a hyperspace of x. So suppose first that this is actually continuous, then I will show that the kernel is closed. So I am connecting a non-zero linear functional if it is continuous with a closed hyperspace. As I have already described that linear functionals, non-zero linear functionals in a vector space correspond to hyperspace. So now continuity will go to closeness, and discontinuity we will take it to dense. So for continuity, you can see if you assume that f is continuous, then this f inverse of 0, this single set containing 0 is closed set in the scalar field k. So f inverse 0, which is nothing but kernel f, will be closed in x. So that's a one-liner. Conversely, if you assume that H is a closed hyperspace, then you can define If you assume that H is a closed hyperspace, then you can define a linear functional f in this way: fx to k by f of ax plus h is equal to fa. So that is actually what, since H is a closed hyperspace, that means the efficiency of H is 1. Its codimension is 1. So any element, I take x from x minus h, then I can write every element of capital X equal to ax plus h, where a belongs to the scalar field. Then I can define f from x to k by f of x plus h is equal to a. And then clearly f is a linear functional on x, and kernel of f will be equal to h. And we can show that this is actually bounded. Because if it is not bounded, then I can construct this sequence, and this will contradict the fact that H is closed. So continuous linear functional is connected to closed hyperspace, and discontinuous linear functional is connected to dense hyperspace. So whenever you have a discontinuous linear functional, then kernel of that discontinuous linear functional will be a dense hyperspace. So here also I have described this result. Let f be a discontinuous linear functional, then kernel of f is equal to h is not equal to x. So if possible, let h be not dense, then h being a hyperspace and kernel, so it has to be either closed or dense. If it is not dense, then it is closed, and if it is closed, then I can show that f is bounded. So once it is closed, then I can show that f is bounded, and this is again will be a contradiction. So I can see that this connection is established. So continuous linear functional in a norm space corresponds to closed hyperspace, and discontinuous linear functional corresponds to dense hyperspace. So one is for closed, another is for dense. So once again, I say, once we are working in a vector space, then non-zero linear functional kernel, they correspond to hyperspace. And once we are working in a non-linear space, continuous linear functional, non-zero continuous linear functional, they will correspond to closed hyperspace, and non-zero discontinuous linear functional, they will correspond to dense hyperspace. So this is what we need to keep in mind. So let me get this. Now I talk of this example of dense hyperspace. So in fact, in any infinite dimensional nonlinear space, there will always be a dense hyperspace, because I can think of a linear functional in an infinite dimensional nonlinear space which is not bounded. So just simply define, since it is infinite dimensional, you get a linearly independent set of vectors xn, then you extend it to a basis, ML basis b of x, and define a function f from b to r by fx equal to n into norm xn, and f of x alpha equal to 0 for all x alpha belonging to this. And since we are working on a vector space and we are working with only linear functional, so any function which I define on a basis, then I can extend it linearly to the whole space. That is the advantage of working with linear functionals on a linear space. So then f is a linear functional on x, but since fxn equal to n into norm xn, so clearly from here we can see that f function is not bounded. So since f is an unbounded linear functional, so I look at the kernel f, then that will be hyperspace which is dense. So there are plenty of dense hyperspaces in an infinite dimensional nonlinear space. Minded in an infinite dimensional nonlinear space. Finite dimensional nonlinear space, all linear functionals will be continuous, so correspondingly all kernel will be closed hyperspace. So geometrically there is a difference between these two hyperspaces, one in finite dimensional nonlinear space and one in infinite dimensional nonlinear space. So finite dimensional nonlinear space, I can visualize hyperspace very easily, that's a closed, but in case of infinite dimensional, that geometry is a little more complicated to think of. So next, next we discuss about two important geometric notions of strict convexity and smoothness. This is what I require for connecting with this, Hahn-Banach theorem. So, convex set is very clear type of thing actually. If you, for every xy belonging to S, this Lxy, that means 1 minus tx plus ty, is actually part of S. So if this straight line segment containing x and y, convex straight line segment containing x and y, that is of the form 1 minus tx plus ty is a part of S, then it's a convex set. So the unit ball of a nonlinear space is always convex, and that comes from this, this triangle inequality. So this is our unit ball in R3. So this is convex. This is unit ball in R3 L infinity norm, and this is unit ball in R2 L infinity norm. These are all convex sets, An example of a non-convex set I tried to give here. You see, if you take one point from here and one, sorry, if you take, if you take 1 point from here and 1 point from here, then you join them, then straight line segment points are actually not inside this set. So this is not a convex set. So the important part is that unit ball of a norm space is always convex. So this is convex set. Then we come to strictly convex space. And if you look at a convex, non-empty convex subset, then a point X is said to be an extreme point of S if for any YZ belonging to S, X is equal to 1 minus Ty plus Tz implies X is equal to Y equal to Z. That means no point in this set is a proper convex combination of any two other points. So X is never a convex combination of Y and Z. Whenever X is a proper convex combination of Y and Z, then X equal to Y equal to Z. So that point is called an extreme point, right? So a nonlinear space is said to be strictly convex if every point of Sx is an extreme point. So if the unit sphere has every point as an extreme point, then it is actually a strictly convex space. So in other words, the unit sphere of the nonlinear space does not contain any straight line segment. So there should not be any straight line segment. As for example, LP spaces for 1 less than p less than infinity are strictly convex, whereas L1 and L infinity are not strictly convex. So this is your strictly convex space, right? So you look at this unit sphere, so there is no straight line segment part of this. But if you look at this unit sphere means the box, not the inside. Unit balls means everything, right? So here unit sphere is this one, this ball, the sphere, and here this unit sphere is this box. So there you can see easily that there are plenty of straight line points, straight line segments on the boundary of this ball. So the unit sphere contains plenty of straight line segments. So this is actually your L infinity norm with R3, and this is usual Euclidean norm in R3. So this is strictly convex and this is not strictly convex. And one more definition I would like to get into, there is smooth point. So an element is said to be smooth point. So if I take this unit sphere, I will say this is a smooth point if there exists a unique bounded linear functional that attains its norm at this point. So geometrically, I will try to connect this. So that will be much better. So here you can say these are all, because you have only one bounded linear functional that is attaining its norm. So this is where, but here it is non-smooth point because there are too many bounded linear functionals. So I'll just go to this next slide, then you can see there is a connection of smooth point with supporting plane actually. So let me describe this, then it will be very easy to understand. So for smooth point, you just keep it in mind, and then we just describe what is this hyperplane connection. So what we said, let H be a hyperplane, then there exists x0 belonging to capital X such that H is equal to x0 plus h0, where h0 is a hyperspace. So translation of a hyperspace is hyperplane. Accordingly, there exists a linear functional f such that kernel f equal to h0. Let f of x0 is equal to alpha. So x can be divided into three mutually disjoint sets as follows. X is equal to set of all x such that fx less than alpha, fx greater than alpha, fx equal to alpha. A hyperplane is said to support a convex set S at a point x0 belonging to S if x0 belongs to H intersection S and the convex set S is contained in either this part or that part. So on the one side it should be lying. So this hyperplane should contain this convex set S only on one part. So it should not be going through that. So let me give you a picture. So this is, if this is the hyperplane, so it is dividing it into three parts. One is this fx equal to alpha, one is this fx less than equal to alpha, one is fx greater than equal to alpha, right? So this is what I am talking of, this all this actually in connection to continuous linear functionals or closed hyperplanes, right? And if you look at this circle, this is a convex set, so and this is the hyperplane at 1, 0, 0. So this is actually supporting this circle at this point. So this point is a smooth point. Now, if you come here, then this point is not a smooth point because there are too many hyperplanes that is actually supporting, and too many hyperplanes supporting means there are too many linear functionals that is attaining its norm at that point. So this connection between smoothness and supporting hyperplane is very important. There exists a unique bounded linear functional f such that fx equal to 1 is equal to norm f, if and only if there exists a unique supporting hyperplane to the unit ball bx and x. So just to see what are the points of the unit sphere which are smooth, you just look at this point in the unit sphere and draw as many as possible hyperplanes passing through that point. And if you see that there is only one hyperplane which is actually supporting, then this is a smooth point. You see, if I take any other line like this one, then this is not supporting, because this convex set S is not on the one side, that is on both sides, this way, that's both way it's involved. So this is the supporting line that is supporting this convex set S. Here also, this is one supporting line, this is another supporting line. In fact, there are many supporting lines. So this is actually not a smooth point. So now you can see all those corner points are basically non-smooth points. All those corner points are basically non-smooth points, and every point on this circle is basically a smooth point, because you can get only one line passing through that point which will support the circle. That's the important thing. So geometrically, these are very nice things to visualize actually. So you can easily see the unit sphere is whether it is smooth, whether it is strictly convex. By looking at this, I can say whether it is strictly convex or whether it is smooth. As for example, if I go back 2 or 3 slides, then I can see, right, so this is, it is strictly convex as well as smooth, but this is neither strictly convex nor smooth, right? There are examples to show that strictly convex and smoothness are actually not dependent on each other. One may be strictly convex, one may not be smooth, and one may be smooth, but one may not be strictly convex. So now I think I have done sufficient this connection of hyperplane, smoothness, and all these things. So maybe I need to go back to this. There are 2 remarks to show that when a boundary linear function can be supporting and when it cannot be supporting, right? So not every linear functional is a supporting, right? So there are spaces, in case of infinite dimensional nonlinear space, there are bounded linear functionals which is not a supporting linear functional. To support a linear, or to become a supporting linear functional, that has to attain a norm. So if I can find a linear functional which is not attaining its norm, then it will not be a supporting linear functional. And of course, you can, in infinite dimensional nonlinear space, you can find those elements. So now we are now in a situation to connect our figures to Hahn-Banach theorem, right? So again, we just remember this circle to sphere. And now let me look at this first. Hahn-Banach theorem. Maybe this is a real vector space, this is complex. I'll go to this one, right? Nonlinear space, right? So what is it saying statement? X is a nonlinear space over K, and M is a subspace of X. F is a bounded linear functional on M. Then there exists a bounded linear functional G on X such that G restricted to M is equal to F and norm of G is equal to norm of F. I am here to connect this with my initial figures. So there is a nonlinear space. So now I take X is equal to R3 with Euclidean norm, right? And I take M is a subspace of X. I take M is equal to, R2. M is equal to R2, this plane. So I'm working on a space as the mother space, and my plane is actually the subspace. And there is a bounded linear functional on that plane. And what I say that I can extend it to a bounded linear functional on the whole space. So let me go back again to the slides. Yeah, now look at this. So whenever I am talking of this mother space, then this mother space is actually R3. So subspace is actually plane. So in a plane, this circle is the unit. This circle is the unit ball of the plane. And I have got this point 1, 0, 0. So there is a bounded linear functional at this point, right? Which is attaining norm at this point. So how do I describe this? So I describe this M is equal to XY0 belonging to R3. That is a subspace of R3. And F is defined by Fxy0 equal to X. Then F is a bounded linear functional on M. Norm F equal to 1. And F attains its norm at 1, 0, 0. Right? So the line is a supporting line. X is equal to 1 is a supporting line of the unit ball at the point 1, 0, 0. So if I look at this X equal to 1 in the plane, so I'm working in a plane. So you can see this line is a supporting line, right? This line is a supporting line. So now you can easily see that there are many hyperplanes containing this line, right? So what Hahn-Banach theorem guarantees? Hahn-Banach theorem guarantees that there will be at least one hyperplane containing that line which will support the unit ball of R3 at the point 1, 0. So actually, when I visualize this in R3, then gxyz equal to x actually is the linear functional, which is nothing but non-preserving extension of this fxy0 equal to x. So this was acting on this xy0. This is basically nothing but R2. This is nothing but R2. So this function was my line. So fxy0 equal to x in R2 was the line, and gxyz equal to x in R3 is this plane. So this is x equal to 1 plane, right? So what I see that this is the non-preserving extension of it. So you can see thus the hyperplane is a supporting hyperplane of the unit ball x containing the line M. So what I'm trying to emphasize here is that given a bounded linear functional on a subspace M, there exists a bounded linear function g on x such that this happens. So this is actually geometrically, if are working on Euclidean space, this is basically what I have described in this geometrical figure. So if you have a circle, you have a bounded linear functional or a tangent line to a circle at that point, then you can find a sphere containing that circle and a tangent plane containing that line, which is actually a tangent to this sphere at that point. So this is actually what is Hahn-Banach theorem. So what actually Hahn-Banach theorem is giving us is actually this is giving that this geometric thing that is happening in with the circle and sphere that can be generalized and continued, and that can be taken far to the concept of nonlinear space. And this, if you have a nonlinear space and a subspace have a bounded linear functional on M, then there exists a bounded linear functional which you can actually go for this. Maybe I should go a little faster now. I will not describe the proof. So this is another connection. This shows that this non-preserving extension may not be unique. So if you go back to this box, then you can see that from, so let me just show you this once again. Where is this box? This was the box, right? This was the box. So from there, I have extended it to this. Right. So you can see, passing through this point, there are too many hyperplanes. Right? So this extension is not unique. But if you look at this sphere, there is only one plane that is actually supporting this sphere, right? So there is exactly one bounded linear functional extension. There is exactly one extension, right? So from this tangent line, you are getting only one tangent hyperplane. Tangent line to the circle, you are getting exactly one tangent plane to the sphere. But in case of box, there are too many tangent planes. So that means this extension is not unique. But why it is not unique? So now you just look at these geometric figures. One is the sphere, which is smooth, nice, and another is this box, which is having corner points, non-smooth points. So that is the problem actually. So for that reason, so if your unit sphere is not smooth, then you have too many hyperplanes there. And so the extension is not unique. And this is what is described in this theorem. So Hahn-Banach extension of a bounded linear functional defined on a subspace of a nonlinear space is unique if and only if the dual space is strictly convex, right? And this is globally. So given any bounded linear functional on any subspace of the nonlinear space, that extension will be unique if and only if the dual space is strictly convex. So this characterizes when every bounded linear functional on every subspace will have a unique extension. But there is another local theorem which characterizes when given a subspace M, when the bounded linear functional on that subspace M can be extended uniquely, right? And that is described in the following theorem, right? Let M be a subspace of a nonlinear space X, then every linear functional on M has a unique Hahn-Banach extension if and only if M part has the Hahn property. And the Hahn property is this, right? So these are not very difficult concepts. So one who is aware of this little bit of functional analysis and this dual space and all these things, these are very simple. So this is the uniqueness criteria for Hahn-Banach extension, right? So I have also illustrated here why this extension in L infinity 3 is not unique, actually, because L infinity 3 is not smooth. Or in other words, the dual space of L infinity 3, which is L13, is not strictly convex. So that is the criteria. So if you look at this, the dual space is to be strictly convex. So here it is not strictly convex. L13 is not strictly convex, so this doesn't happen. And I have just described it. Yeah. Oh, so now another important version, or sometimes it is called geometric form of Hahn-Banach theorem. That means when you can separate two non-empty convex sets by a hyperplane, right? So let me first begin with this figure. I think that will be okay. So now you see this is set B, right? So set B is the collection of all x such that collection of all xy such that x is greater than 1, and A is the collection of all xy such that x is less than equal to 1. So both of them are convex sets, A and B, disjoint convex sets. So you can separate them by a hyperplane that is x equal to 1, right? But if one of them is not convex, then you cannot separate them. As for example, if you have B like this, so you can see B is this. B is the collection of all those points in this yellow shaded region, which is surely a convex set. But if you look at A, is the collection of all this blue shaded region, then this A is not convex once again. So you can have this point and this point in A, but the straight line segment is not here, is in B. So A is not convex. So one of them fails to be convex, then you cannot separate it by a hyperplane. So how many line you draw through this area, but you cannot separate A and B. So that means your A will not be on one side and B will not be another side. Separation means you have an hyperplane where this line will act as a boundary between these two sets. So A will be on one side of this line and B will be on another side of this line. So this is what is the definition. So let me just get into this. So we say that there exists a closed hyperplane which separates A and B. That is, there exists F belonging to X star such that FA is less than equal to C less than equal to FB for all AB belonging to B. So you have a point C such that on one side of which FA, all these points A is lying, and another side all the points B is lying actually. So this, Fx equal to C actually is your closed hyperplane. Fx equal to C is here acting as a closed hyperplane. So I have chosen those examples. I have just shown in you figure. This is your A, this is B, then this 1 is this actually. Fx equal to 1 is the hyperplane. That means x equal to 1 is the fxy equal to x. That means x equal to 1 is your hyperplane, which is separating A and B. Now this separation can be strict. This separation can be strict in the sense that the hyperplane is at a positive distance. So that means you have this, there is a C such that FA less than C less than FB for all A belonging to B, B belonging to B, or something like that. Yeah, so maybe you can write this is C less than D, yeah. C, FA less than C less than D less than FB. So to show that there is actually zone where it is actually separating those distances. And for that, only convexity and openness will not be sufficient. So last theorem, if you look at this, so you have this necessity conditions that both A and B should be non-empty and disjoint convex sets, and one of A or B is open. So one of A or B is open, then you can separate it. But if neither of them is open, then you cannot separate it. I will come to that. That example I will be showing you after a few minutes. So now if you come here, if your A is compact and B is closed, then there exists a closed hyperplane which is strongly separating or strictly separating this. So that part is there. And let me get into this. The following example shows that convexity alone is not sufficient actually. If you look at A and B only convex, no openness, or neither compact or closed, there's nothing. So if you only ensure compactness, then this may not be sufficient to separate. And that's a very nice example. So if you are in an infinite dimensional linear space, just look at Hamel basis B, which contains elements x1, x2, xn. So you are looking at all those elements S, for which this highest coefficient is actually greater than 0. AK is greater than 0. So for example, x1 plus x2 will be there. x1 minus x2 is not there because x2 coefficient is -1, but x1 plus x2 will be there. Also, all those elements for which highest coefficient is positive, then it is. And you can easily check that this is a convex set. And definitely 0 does not belong to S because coefficient is always strictly positive. So what we claim that this set singleton 0 and S, although they are disjoint and convex, they cannot be separated by linear functionals. But because if such a linear functional exists, you can see that F0 will be always equal to 0. And if they want to separate 0 and S, then Fs is either greater than equal to 0 or less than equal to 0. So if you assume that Fs is greater than equal to 0, for the time being, we assume that Fs is greater than equal to 0. Now you look at this element. For any n, axn plus xn plus 1 always belong to S. And for any real number a, because I have chosen this coefficient 1, which is positive. So Fs greater than equal to 0 will imply this is positive. Now we can see that for every a, fxn plus 1 is greater than equal to 0, and that will force fxn has to be equal to 0 because there is no such. These are all scalars. Fxn is a fixed scalar, fxn plus 1 is a fixed scalar. So for every a, if this has to happen, then that means your a has to be, this fxn has to be equal to 0. So this implies that f is equal to 0. So that means what? F0 equal to 0 and f of xn is equal to 0. So f becomes equal to 0. So there is no non-zero linear functional which is separating these two sets because we don't have any convexity. Actually, we need some interior point, right? So that is more than enough, but there is no interior actually. So that's why this is failing. So this separation is not working if we are only working on. So if A and B are both convex sets, then I need at least openness of one of A or B. And if I want to go for strict convexity, then I need one of them has to be compact, another has to be closed. Otherwise, it is not done. So this is what is this separation geometric form of Hahn-Banach theorem. So maybe I don't know. Yeah. How much time I can take, Debashish? More?
Yes, sir. You can take. It's only 11:30. You can take 15-20 minutes. No problem.
Okay, fine. Just I'll then just describe this some things related to operator version, and then I'll go to this very brief introduction of Birkhoff-James orthogonality, which is my area of research nowadays.
Yes, sir. Yes, sir. You can take. Actually, we started late also, so you can take more time.
Okay, fine. Thank you. Yeah. So now, once this analysis is done for this linear functional part, so the question naturally arises. Suppose I have a nonlinear space X and I have a subspace M, and I have a bounded linear operator defined on M. Right? So I have a linear operator T from a subspace M of X to any other space, say Y. So can I extend that bounded linear operator T from X to Y? So far the Banach space Y was actually our scalar field because we are talking of all linear functionals. So naturally mathematicians have a curiosity to know what happens if we remove this scalar field or replace this scalar field with an arbitrary Banach space. So that's the next question, a natural question actually. So what will happen to it? So one definite positive answer in this regard is that if your M is a dense subspace, so that is very true. So suppose that M is a dense subspace of a nonlinear space X, and Y is any Banach space, and T from M to Y is a bounded linear operator. Then there is a unique bounded linear operator T1 from X to Y that agrees with T on M and norm T equal to norm T1. So it's basically very easy to see that since your Y is a Banach space and M is a dense subspace, so for those elements, actually for extending T to T1 on X, what we need to do, we need to see at all M closure. So already T is defined on M, so I am concentrating on all those elements which are in closure of M, but not in M. That means I am looking at all those limit points of M. So if I take any point X which is not in M, that is a limit point of M. So I just take, say, X0 is a point in X which is not in M. So I can definitely find a sequence Xn from M such that Xn converges to X0. So I'll define T1 of X0 is equal to limit of this Txn. And that liberty, that Txn I'm going to define, I can show that this Txn actually becoming a Cauchy sequence in Y. And since that is a Banach space, that will converge to some point. So here you need this concept of Banach space also. So whatever the case, in case of bounded linear operators, if the subspace is dense, then you are done. There is nothing more to be done. So this is over if your subspace M is a very special subspace which is dense in X. But in general, what happens if your subspace M is not dense? Then there is a nice thing. Yeah. So I need this. So these are the famous theorems. For every Banach space Y and every bounded linear operator T from M into Y, there is a bounded linear operator T1 from X into Y that agrees with T on M. The closure of M is complemented in X. So if you have a Banach space X, and if you have a subspace M of X, and if you know every bounded linear operator from M into Y, this Banach space Y, as an extension from X into Y that agrees with T on M, then this closure must be complemented in X. So M closure should be complemented in X. So it is connected to this complementary subspace problem in a sense. Yeah. So now we already know that there are Banach spaces and there are closed subspaces which cannot be complemented. As for example, the space C0 is a non-complemented closed subspace of L infinity. So these two will not be equivalent. So that means there will be some operators which will be on C0, but that will not be extended to L infinity. So this is a low bounded linear operator from L infinity onto C0 maps each element of C0 onto itself. So in fact, there exists no bounded linear operator from L infinity onto C0 that maps each element of C0 onto itself. So in a sense, what does it imply? It implies that if you look at the identity operator from C0 to C0, then you cannot extend it to L infinity because there exists no bounded linear operator that maps. And this is connection with this one. Right? So from here, you can come to here, and from here, you can conclude that the identity operator on C0 cannot be extended to a bounded linear operator from L infinity onto C0. So that means there are operators on Banach spaces, subspaces, which cannot be extended continuously to the whole space. So that means your Hahn-Banach extension, which was true for linear functionals, that is not true for operators. Hahn-Banach extension, which was true for bounded linear functionals, that is not true for bounded linear operators. The most important part you need to remember is that boundedness, actually. Otherwise, you see, if you forget about this boundedness, what happens? You give me any subspace. You give me any subspace of a linear space, and you give me any linear operator on that subspace. I can always extend that linear operator to the whole space. Because I will just look at the Hamel basis of the subspace M that will be linearly independent, and I will extend it to the whole space, and I can define a linear operator which agrees on M with the original operator, and outside M I will define it like anything. So I will just make sure that the basis part which is coming from M, there it coincides with the original operator, and on the part of the basis that is not in M, I can define it as 0. Or I can define it something else, because I am not concentrating on the boundedness or unboundedness. So linear operator extension is always there. That's not a big question. The problem is when you are working on a nonlinear space. So that becomes important. If you are working on a nonlinear space, then that's the problem. Even if you look at this Hahn-Banach theorem for real vector spaces or Hahn-Banach theorem for complex vector spaces, then you will see there is a sort of functionals on the original space, and the subspace has a connection, and the functional on the subspace has some sort of boundings on it through this original space functionals. So you have to remember that. Because if you are working on a linear space, on any subset, you don't have to go for a subspace also. On any subset, if you have a linear operator, on any subset, if you have on any subspace, you have a linear operator, then you can definitely extend it to the whole space. Because that's purely algebraic. I will just go to basis, extend basis to the original space basis, then I got it. So no question of this boundedness or unboundedness there. But once it is boundedness, then there is a problem. For this linear functionals, it's fine. The bounded continuous, every bounded linear functional on a subspace can be extended to the whole space, but linear operator, it is not true. That's not possible. And if it becomes true, then the space becomes actually Hilbert space. That is what is my next theorem. Yeah, you can see. So this is an infinite dimensional Banach space has the extension property if and only if X is a Hilbert space. What is this extension property? It says that M be a closed subspace of X, X is a Banach space, then M has a property P if for every Banach space Y and every bounded linear operator T from M to Y, there exists a bounded linear operator T1 from X to Y such that T1 X equal to Tx for all X belonging to M and norm of T1 equal to norm of T. So we say that X has the extension property if every closed subspace of X has property P. And it can be shown that, in fact, Lindenstress and Jeffrey showed that an infinite dimensional Banach space has the extension property if and only if X is a Hilbert space. Again, if you come to Hilbert space, then you can see this proof is very simple. Actually, if you have a M closed subspace, so in a Hilbert space you can complement it. So H Hilbert, if you have this Hilbert space X, then you can write X is equal to M direct sum M part. So you have this liberty of writing X is equal to M direct sum M part. So you have a linear operator defined on M. So you can extend it to this by defining this element on M part is equal to 0. No matter. I can have a linear operator. So if T is the linear operator from M to Y, so I'll just define T1 of X equal to Tx for all X belonging to M, and T1 of X is equal to 0 for all X belonging to M part. So for Hilbert space, there is, I think we all know why it is happening actually. But if the Banach space always have this property, extension property, that means every subspace, every closed subspace, and every bounded linear operator on that can be extended continuously to the whole space, then it has to be a Hilbert space. So that is another important reason. So this is how I think I have tried to cover all this related to operator version of the Hahn-Banach theorem. And now I would love to move to this application part, which we are doing maybe for last 7 to 8 years. Devashish knows it. I think so. Yeah. So this is what the most important part of this theorem is, this one. So I will just finish it in another 5 to 10 minutes. So just motivate you geometrically, what is Birkhoff-James orthogonality, right? So you just come here. So this is school geometry, nothing big. Yeah. You see X is orthogonal to Y1 because angle between X and Y is 90 degrees. So that's fine. Cos 90 is 0, right? So inner product X and Y1 is 0, right? But this X is not orthogonal to Y2. You can see geometrically, right? So now you think of this as your unit sphere, right? This ball as unit sphere. Now you look at the straight line passing through X parallel to Y1. Now the straight line passing through X parallel to Y1 is this one, right? And this is, I have assumed to be unit sphere. So all the vectors or elements on this sphere as norm 1, all of them inside as norm less than 1, and all of them outside as norm greater than 1. So now if you look at these lines, if you look at or consider all those points which are on this line, so you can see easily this one is the smallest norm and all other norms are greater than 1, right? So norm of X plus lambda Y, which is actually the points on all these blue lines, they are always greater than equal to norm X, right? And now if you look at this Y2 vector, then norm of X plus lambda Y2 are the points, X plus lambda Y2 are the points on this line. And you can easily see this X is not the smallest norm vector of all X plus lambda Y2. In fact, there is one such vector which is the smallest one, right? So norm of X plus lambda Y2 is not greater than equal to norm X for all lambda. But norm of X plus lambda Y1 is greater than equal to norm X for all lambda. So this motivated Birkhoff and James to define orthogonality in a Banach space. So they have come out of Hilbert space and they've defined orthogonality in a Banach space. The main idea of defining this orthogonality is to study geometric properties of Banach space with the help of the notions of orthogonality that are actually prevalent in Hilbert space. In case of Hilbert space, this there is this X is orthogonal to Y if and only inner product XY is equal to 0. But how do we define orthogonality in Banach space? We define like this. We say X is orthogonal to Y if and only for any scalar lambda norm of X plus lambda Y is greater than equal to norm X. And it has it is equivalent to inner product xy equal to 0 if you are working in a Hilbert space. So this notion is very important notion in the study of geometry of Banach space through orthogonality, because you have many results on Hilbert space through orthogonality, and we can now see whether they are going to be true in Banach space, whether they are not true, and why not true, and what is the conditions we more need to put on, and all these things. These are very nice results, and there are 2 or 3 classical papers by James in which we describe the entire geometry of the ground space Banach space X, right? So, and this N-Banach theorem is used here actually. Fine, yeah, let me get into this. Yeah. So given a nonlinear space, you take any non-zero vector x, there exists a hyperspace H such that x is orthogonal to H. So this is where you need Banach theorem. This is where you need Banach theorem. There is a nice connection of orthogonality. So you can say this happens if and only if there is a bounded linear functional for which fx is equal to norm x and f of h is equal to 0. So we can show this actually. And through this bounded and this linear functional's existence is actually coming through Banach theorem. So there is the importance of Banach theorem. So even if we have this concept of Birkhoff-James orthogonality, which is very nice, we have a very nice geometric motivation for that. But to work with this, we need this Banach theorem very much. And there are many classical results on the ground space X, I'm saying you, which is actually dependent on Banach theorem. And these are all studied by Birkhoff and James, and mainly James. Mainly James have studied these geometrical properties, many geometric properties, the reflexivity of Banach space through orthogonality, then characterization of many other properties in this, inner product space characterization and many others, strictly convex characterization. All these things have been studied by this, James in his classical papers. And what we are doing actually, we are extending it further in the study of the geometry of operator spaces, right? And that's more complicated one, right? So recently we have been studying this, and we have done some very good results. Actually, at least we are satisfied with that. So characterizing some geometric properties of this operator space. Operator space means you have a Banach space X, or you have 2 Banach spaces X and Y, and you look at the collection of all bounded linear operators from X to Y. So you look at this BXY, which is the collection of all bounded linear operators from X to Y, and then, so instead of looking at the elements of the ground space X, now we are looking at operators T from X to Y, and then we are studying some very important geometric properties of BXY through this Birkhoff-James orthogonality, right? I think I need to conclude this session with the following references. I will conclude this lecture with the following references, and I will find some of our references along with the work by James. Yeah. So these are James' papers, very nice papers, and these are what we are going to do is, yeah. These 2 are our recent papers. One is in Journal of Operator Theory, one is linear algebra applications, and we have done actually too much of research in that area. And I must thank you all for your patient hearing. I don't know how much you like it. In case you have any questions or anything related to this lecture, you can feel free to write to me through my email or whatsoever. Yeah. Bye. Thank you.
Thank you very much, sir. Yeah.
I need to, yeah, I can see.
Yeah, you can see us now. Okay, so thank you very much, sir, for this wonderful presentation. There are lots of feedback from the participants as well. I'll flash those on screen. I think you can see. Can you see something written, sir?
Yeah. I can see Priyabroto is written very, very nice words. Thank you.
Okay, so the questions also I'll pop them up on the screen, and yeah. So before taking up the questions, I'll invite our student Sumli, who has joined us earlier. She could not join because of network problem.
Yeah.
Now she is there with us. Sumli, can you hear me?
Yes, sir.
Okay,
Good morning,
so
everyone.
yeah, you
Good
can
morning.
Good
continue.
morning, everyone present here. Good morning,
What?
sir.
Good
Yeah, you
morning.
can.
Good
Sir,
morning.
earlier, due to network congestions, I was unable to read out your biodata, sir.
Yeah, oh, I got that. I got that. Devashish read it out in details.
Now she will deliver a vote of thanks. Yeah, she
Yeah.
prepared it quickly. Okay, go on.
Sir,
Yeah.
I'm Sumli Varman, studying in sixth semester, BSc Mathematics Honors from Gurucharan College, Silchar, sir.
Yeah.
So today I, on the behalf of whole of the organization of this event, want to extend my heartiest vote of thanks to all the speakers for gracing your important work through valuable lectures and sharing with us your findings and opinions today. Secondly, I want to thank all the participants from all over India and abroad for attending this webinar series. I also extend my heartiest thanks to Google for being such a nice platform for everything, starting from creating registration forms, generating certificate to video streaming through your YouTube. Also providing other resources necessary for organizing this webinar. Also, many thanks to StreamYard for providing an excellent platform for conducting this webinar. Also, heartiest thanks to the principal of Gurucharan College, Silchar, Dr. Bibhash Dev, and IQAC coordinator, Dr. Rajashri Paul, because without your support, sir, I don't think this event will be the successful one. Last but not the least, I would like to thank the professor of Department of Mathematics along with the students for your immense support. Um, Thank you so much, Honorable HOD, sir, Department of Mathematics, Dr. Biplab Chaudhary, and other faculty members for organizing the webinar. Thank you so much.
Yeah. Thank you very much, Sumli. So I'm putting you backstage now, and we'll
Yes, sir.
continue with some more feedback. So yeah, we have our guests. First of all, I'd like to add Uday Shankar sir. Yeah, sir, you are live on screen. Please unmute yourself. Yeah. Yeah, sir. Can you hear me?
Yeah. Thank you.
Yeah.
Okay.
Yeah, if you have some, so I think you have to unmute yourself. Yeah.
Yeah.
Yeah, sir. I would like some feedback from you. Okay, I think sir is experiencing some network problem. Okay, so let me go to Navakanto sir from Assam University. Yeah, hello sir. You
Yes,
are on
yes,
screen now.
yes, Devashish. Yeah,
Yeah.
my also I was using GeoPad, so I have
Okay.
exhausted my data there. So now I am joining by mobile.
Okay.
I have
Okay.
mobile. I am joining.
Okay, sir.
Okay, so
Yeah.
first of all, thank you, Kallol sir, for your wonderful talk. It was
Thank you.
indeed a very pleasant one. I wish I had listened to this talk when I was doing my MSc.
Thank
Then
you.
it would have been very motivating for me. So
Thank you.
I want to know from you one thing, that while doing these results in a class, how you would like to go about the proof of this Hanbanak theorem. Generally, when the problem we face is that when we try to prove Hanbanak theorem in a class, since it is very long, the students after some time the students feel very started feeling very boring. So how do you like to make it more interesting for the students?
Yeah. But you see, until and unless you put or bring some geometrical part into these theoretical things, it becomes very difficult for students to consume things actually. And so you need to anyhow have a connection with the geometry of what actually going in. Actually, ultimately, mathematics is what we see. That's what we are generalizing, and how much we can take it to this abstract level, all of these things, right? So if you can connect with just, this normal geometrical things like this, what I've shown, this box and this square and this sphere and circle and all these things, and how you see it. Actually, I was also actually baffled with this Hanbanach theorem for a long time. I wanted to visualize it. I was just thinking of how to motivate students actually. So I will just enter into the class. I will say, you have a circle, you have a tangent line, you have a sphere, you got this tangent line. Do you understand this? Everybody will say this. So this is Hanbanach theorem for me. This is your Hanbanach theorem. Now I connect you to this. So, and slowly I try to develop all these things. So, this we have got this opportunity in functional analysis where I am working on, or I am teaching actually, where we can bring these geometrical parts into play. Actually, geometrical aspects. If you bring these geometrical aspects into play, then it becomes very nice, interesting. Of course, I can. I know very well that everything which is analytically true cannot be looked into geometrical. There is a limitation actually. Like I have talked about dense hyperspace. You cannot visualize it in geometrically because in finite dimensional cases every hyperspace is closed actually. So how do you see dense hyperspace? You cannot see, but at least we can see closed hyperspace. We can motivate students with that part. So that to me, I feel actually you have to have a geometrical role in this. As much as possible. It's not possible in every area, I know that very well, right? So, but this Hanbanach theorem, or where we are working, we are fortunate enough to bring some geometrical factors into that, and that motivates students actually. So, what happens when I talk, you listen to me, but when I show you something in figure, then it appeals to you much more. And for students, that's more important. What they see, they can visualize actually, they can understand, or they can feel much better, rather than they listening to this, let X be a Banach space and M be a subspace of X, they'll forget it in 2 minutes. But when I put in its figures, they will remember it for long. I believe if someone connects this Hanbanach theorem to this part, then he will never forget it. But what is happening there actually, that's the important thing. But this analytical things have this much dominance over geometrical things. Analysis you breaks your geometrical intuitions, so everywhere you cannot bring it, right? So there are some limitations.
Thank you again.
Thank you.
So I have one more little query, small query. That in the extension of the Hanbanach theorem to arbitrary Banach spaces, you have given 2 equivalent conditions. That if the closed subspace is complemented,
right.
There is extension. So in that first condition, that the norm will also be preserved. You have not mentioned whether the norm will be preserved or not. I think the norm will also be preserved. No, norm of T1 should be norm of equal to T.
No, in the first there is no question of we're not showing of non-preserving extension. We are just saying whether it will be extended. Second one is the non-preserving one. Extension property is actually including norm one.
Yeah, no. My query is that in Hanbanach theorem, we want that the norm of the extension is also preserved. But
there are two
your
parts.
equivalent condition,
there are 2 parts in. First of all, whether you will be able to extend it or not, and second, whether it will be extension will be non-preserving or not.
Yeah.
So if
in the case of general Banach space, can we preserve the norm or not?
No. We can never. But then it will become a Hilbert space. Then it will become a Hilbert space.
Okay. Yeah, that's right. Thank you.
Thank you, sir. I'll put you backstage now.
Yeah. Sure.
So I think Uday sir has joined again. Yeah, hello sir.
Sorry, actually I got disconnected. Yeah. I got disconnected, and after several attempts, I could connect. Yeah.
Sir, you can continue. Yeah.
So thank you for the nice presentation, Kallol.
Thank you.
Hello.
Yeah. I am listening to. You are audible to me. I can listen you very clearly. You just go ahead.
Hello.
Yes, sir. Sir, you are audible. We can hear you. Maybe sir cannot hear us or what?
No, I can hear him. Yeah.
I mean, Uday sir, maybe he is having audio problem.
I can see he has written one comment actually. So
Yeah.
I just
Okay.
read it out.
Yeah.
Thank you for such a nice presentation. Is there any other form of orthogonality in Banach spaces which is equivalent to orthogonality of vectors in Hilbert spaces? Yeah, there are many other forms of orthogonality. You know, Roberts orthogonality, then this isosceles orthogonality, Pythagorean orthogonality. There are many other orthogonalities, but none of them are as important or as beautiful as Birkhoff-James orthogonality, because Birkhoff-James orthogonality is the most important one in terms of geometrical motivation, as well as in terms of applications to the study of, this geometry of higher objects, like, operator space or something like that. Yeah.
Okay. Okay, sir. We have Dr. Anirban Roy also with us. I am adding him. Yeah, Anirban sir, you are on screen. Yeah, you can put forward your comment.
Yeah, fine. First of all, many thanks to Kallol sir for such an wonderful presentation.
Thank you.
I don't have to say anything about or no question about it, but I want to add something to the initially what biography or the way they have written about read about Kallol sir. Might be that is not written in the biography. Well, he is also Kallol sir is also from GC College. We all are from GC College, passed out. I'm sure it is not written in biodata.
Yeah.
The fact is that our batch, we passed out in 1999. We all are, by default, we have been motivated or we have been inspired by these figures. Kallolpal, Biplochoddi, Jivannath. We had these three figures always in front of us. So I think whatever mathematics we have done, it is because of the great intelligence, great motivations are provided by these genius mathematicians. And today, as Kallol sir has started his talk, that he mentioned he has visited the place of Banach. That shows the passion, because he is doing his research on the Banach space or nonlinear space, and when he has gone to the place where that person's house is, they feel like I'm also to some extent blessed in that way, because we have been grown up doing the hero worship to this Kallol Pal. We know this Kallol, that much brilliant, meritorious.
Thank you very much.
Probably in all our classes in GC College, whether it is Simanta Datta sir or PM Pranana Choddi sir, they always used to quote, about Kallol did that, Biplov did that. So I also have the blessings or opportunity to visit Kallol sir's house in Calcutta. And it was really wonderful to listen to sir for after a long time for me. And I'm really fascinated. I'm thrilled to see his fascination towards geometry. Today's talk also, sir, connected to geometry and such a beautiful explanation about that Hen-Banach theorem, so nicely. Some comments also people given, they are going through or reading first time, but the way sir has presented. I also have one excellent learning from Kallol sir. I remember, I'm sure sir does not remember that. When I met him first time, he was talking to me about the smoothness of the curve or the differentiability condition over the curve. And he asked me, what do you mean by smooth of the curve? And I instantly given that it is differential everywhere, all those things. I said, no, I don't want all those things. You tell me what you understand by smooth. I was not able to answer that. Then he said, you pick. If you can pick it, it is not smooth. And instantly has given the modulus X definitions. After a few days, I have been absorbed in TIA for Bangalore. So and then my connection is got disconnected. But I found in TAFR everybody talk like that. They talk about geometry, they talk about analysis, but hardly they talk about the proof or anything. They just talk about geometry and drawing and all those things. So somebody has mentioned now that I wish I could have got this lecture during MSc time. Yeah, this is very true. More people get this kind of exposure to that great lectures of Kallol. It will be really good. So my many thanks to Kallol sir once again. Thank you very much for motivating us. Thank you very much for giving us the what is called mathematics in a proper sense, and for guiding. And I think all sincere people till date they have the hero worship towards you. Thank you very much, sir.
Not like that. Yeah.
Okay.
We must thank Devashish for that. Actually, he's doing.
Thank you very much.
I can see Devashish in myself. Actually, had I been in GC College, I would have been like to be like him. Actually,
You are my inspiration. So you are my role model.
Yeah.
So thank you, Anirban sir. I'm putting you backstage now.
I'd like to show. I'd like to show one thing, Devashish. This is what this in the memory of Stephen Bannock. Actually, Polish Academy of Science or Polish government has actually given this in the memory of this when it was actually this 100th year of. This is the picture of Stephen Bannock. Am I? If I am putting it right, I don't know. Yeah.
Yeah, it's visible.
Yeah. This is €2. This was given to me as a gift by a Polish mathematician.
Wow.
So when he knew that I am working on Bannock space.
So we have a comment from Professor M.B. Rege. I asked him to join us live, but he has some network problems. Yeah, you may. He's from Nehu, Northeastern Hill University. So he has attended your lecture now. And can you see the comment? Can you see the comment there on your
comment? Is that Professor?
Professor M.B. Rege.
No, I cannot see.
No, I have flashed it on screen. Okay, I think you have not closed the screen sharing option.
No. It's still on. I have to close it, no?
Yeah, you close it.
I have closed it. Yeah, I have closed it now.
So there is a comment. Yeah, there is a comment there which is on screen. Can you see on screen?
There is some Devi, Ibmael Devi.
I think. Yeah. It's his wife. He has written it from his wife's account.
Okay. Yeah.
He's also a mathematics faculty.
Okay.
Yeah. So Professor
I can
Kallol
see.
reminded me of one semester course on functional analysis delivered by Mrs.
Singh in Mumbai University 1965. Oh,
brilliant mathematician.
Thanks for such a nice comment. Actually,
I asked him to join, but he had some network problems, so he did not join. So we also have Bishwajit Dev sir with us. Bishwajit sir, if you can hear me, would you like to join? Yeah, probably he's not there. Yeah. Okay, then we can take up some questions from the participants. There are several questions actually. Let us begin. Yeah, so this is one question. Is it useful? It's from Rajdeep Dhar, probably a student. Is it useful for the study of astrophysics?
Yeah, definitely. This functional analysis, quantum mechanics, and this astrophysics and all these things, these are all unbounded linear operators and all these things. So this is the functional analysis have very nice connections with this physics, So yeah, definitely, indirectly, definitely, yeah. Exactly not this lecture, definitely not.
Okay, sir. And we have I'm just searching. Okay. This is a comment probably.
Yeah.
Okay. Yeah, this question again. Mukesh Kumar Biswal, what is the difference between Hahn-Banach theorem and extension Hahn-Banach theorem, and how can you use this in a real life problem?
I don't think this Hahn-Banach theorem and extension Hahn-Banach theorem, I think they are same actually. We are talking of extension of the bounded linear functionals defined on the subspace. That is what is Hahn-Banach theorem. There is nothing different to be. I have never heard of something called extension Hahn-Banach theorem, right? So this is Hahn-Banach theorem, and it is focusing on this extension of bounded linear function on subspaces of it. And as you know, this functional analysis is applicable in so many areas and so many subjects, different parts of mathematics and different parts of science, engineering, and all these things. Everywhere it is this real life problem. You can just go on counting all these things. Many. But in this short time, it is not possible for me to.
Yes. So we have another question from Dilip Bora. Is Hahn-Banach theory applicable in fractorial or I think it's fractal geometry?
I think it should be fractal geometry. But as far as I know, no such, nothing as such.
Okay.
There is a famous article on this Handbanach theory by Lawrence Bachman, actually, and Bachman and Narisi's book is there, actually. So if anyone is interested, he can just Google search it. You'll get this all possible extensions, all possible ramifications, applications in various branches. You'll get it there. Yeah.
Okay. So this is another question, Devadri Guho. Can this theorem be extended to n dimension?
Definitely, we are going to infinite dimension, actually. And to mathematicians, n dimension is very small thing. Very small thing.
Yeah. Okay, and then there are some more. Let me see. This is a comment. Okay. Yeah. Okay. What is this question? Mukesh Kumar Biswal. What is the difference between function, functional, and operator? Please explain. Probably it's from a student.
Yeah. So if you have a set X, and Y, so if you talk of a correspondence between elements of X to Y, then it is a function. Any correspondence between X to Y only with the one condition that one element cannot move to more than one element. So it should not be a diverging arrow type of thing, right? So exactly one element from the X set X can move only to one, not more than one. So that's the definition of basic function. So now if you come to this, this linear space or vector space, then you have the definition of functional and operators. So if you have a linear space X, and if you are working from X to Y, where Y is another vector space arbitrary, another linear space arbitrary, then it is an operator. Operator may be linear or may not be linear. And if your domain is X and the range is not Y, but this range is the field over which the vector space X is considered. So if you are considering X over real field R, or you are considering X over complex field C, and if you're looking at a function from X to R or X to C, then it is a functional. Functional means your range is actually scalar field. Operator means your range is arbitrary vector space. But function means it can be arbitrary set X and Y, right? And you just add linear or non-linear, whatever you like to that.
Yes. Okay, sir. So we have another question here. Can you explain? It's from Dipankar Shaha. Can you explain complementary subspace by giving examples?
Yeah, surely. But it's very simple. Suppose you are working in R3, right? So if you are working in R3, you look at this XY plane, right? You look at this this XY plane. Then if you look at this XY plane, then you look at this Z-axis, right? So this complementary subspace means this when you are looking at this XY plane, that means R2, then R2 directs this third vector Z-axis spun by Z. That is actually giving you the whole space back. So complementary subspace means what? If you have a vector space X, and if you have a subspace Y, then can you write X is equal to Y direct some Z for some subspace Z, right? So that is the main thing. If it is done, then you can say that Y can be complemented. If it cannot be done, then it cannot be complicated. So if you have a Banach space X and you have a subspace Y, if you can find Z such that X is equal to Y direct some Z, then you say that Y can be complemented. If there is no such Z for which X is equal to Y direct some Z, then Y cannot be complemented. And to visualize complementary subspace, you can look at this space R3, look at R2, then you can complement to Z. Or if you I have described or I have explained in this presentation, if you look at C0 in L infinity, C0 is not complemented in L infinity.
Yeah. Thank you, sir. So we have another. It's about books. Ramachandra Padhi. Kindly tell me some books for this topic. I have already B.V. Limaye. Tell me some other.
You can go for this, Bachman-Narisi, functional analysis, Bachman-Narisi, or you can an easier book. I have never seen a book which is easily written than this one in any topic. That is crazy, crazy functional analysis. So, or you can go to this Bachman Narisi, or you can go to this Kesavan book is there, this professor from IMSC. So there are many books on functional analysis. Sundar book is there, and Kesavan is there. Yeah, there are many books. Yeah.
So this is a compliment from one of the participants.
Yeah, I think he is from abroad. Yeah.
Most probably from Kerala.
Oh, yeah. Okay.
Thank you.
Francis. Yeah.
Okay, I asked one of the question. There are some more. Okay. Just let me check if there are some more.
Yeah.
Yeah, there is one. I've got this. I'm putting it on screen. Devadri Guha. Can we extend this theorem? Oh, okay. So I think it was already taken. Can we generate any 2D, 3D structure in higher dimensional form? I'm not clear. What is this?
Yeah, I'm also not too much clear about. But we can actually extend this to infinite dimensional spaces. You need only Banach space. Only you need one algebraic structure, another norm, but nothing more, nothing less.
Yeah. Okay. So these are some comments. I'll also look forward. Okay. So this is also another comment from Rege sir.
Oh, thank you very much.
Okay.
Atawar Rahman.
Okay. Okay. One more question. I think it's related. Earlier it was it's again about books.
Yeah. You can if you are reading it for the first time, you can go for this Crazy. Then slowly you can go to this Bachman Narisi, then Conway, and some books by Kesavan, Sundar, and all these things are there.
Yeah. Conway's
But
book is quite tough. I find it very difficult.
Yeah. But that's why I said if you are the first time reader, then you must go for Crazy, then Bachman Narisi, and then you slowly lift yourself up.
Yeah. Of course, Conway's books are really classic books.
But you get very, very, very important results there. Actually, it's But there are so many things in between the lines in those books. You have to crack between the lines.
Unfortunately, he expired a few months back, right?
Conway, I don't know that. Yeah.
Yeah, there was a news, if I'm not mistaken.
Okay, maybe. Yeah.
Let me see if there are other questions. So there are lots of compliments. Thank you to all the participants for those compliments. Okay. Yeah. So almost we are done. So I'd like to request all speakers and as well as you to please stay back. I'm going for a live feedback session from the participants. So I'll just take some time. As of now, I'm putting you backstage, sir.
Yeah, not an issue. So Anirban told me to share it. No, I don't want to say anything more, and I will share it with you so that you can share it.
Most of the participants are asking for the slides.
And if there is anything that logical flow in terms of typos and all these things, that participants should take care of it. It is not the responsibility of the writer. I could found one actually in definition of norm. There is a one typo actually. So I'll try to correct it and then send it to you.
Okay. Okay. So thank you very much, sir, on behalf of the Department of Mathematics for the wonderful presentation.
I thank you. Thanks goes to you actually. You are doing such a wonderful job sitting in Silchar.
So, sir, please stay back for some time. I'm putting you backstage. You can see the screen. So thank you. Okay. Thank you. Yeah, there was some electricity issues here. So I was thanking our electrician of our college, Diponda, for managing everything. Yeah. So I would like to share my screen here for a live feedback. So participants, please stay back with me for some time. I'll just get back. Yeah. Okay. I'm sharing my screen here. Okay. Yeah. Okay. I'm sharing my screen here. Entire screen. Yeah, I think it's visible. Yeah. Kallol sir, can you see the screen? My screen?
Yeah, I can see. I can see. Yeah, I can see you on the left side and the screen.
Yeah. Okay. So I'll just explain to the participants what is happening.
I can see. I can see you on the left side and the.
Yeah. Okay. So I'd like to request all participants to kindly see the instruction which will appear on screen. So in your mobile browser, you can just go to the address www.menti.com. I'll just I'll just post it here, menti.com. Yeah, so you can see the name of the website I have posted here. So please visit this website. You can go out of your YouTube video for some time and please visit this website, and the rest instruction will be given on the screen. I'll share my screen, so other instruction will be given on screen. So just you need to fill up some feedback. So there are 3 questions I would like to, and those feedback will appear live on screen. So let me see if it works nicely. Okay, so I'm going to present this. Yeah. So you visit menti.com and use the code 97. It will ask you for a code, and you can use the code 9757845. It's visible on screen. Yeah, on your screen you can see. You go to www.menti.com and use the code 9757845. It will ask you for some code, and after that this particular question will flash up on the screen, on your mobile screen. So you may answer that question, and then I'll go back to the next question. Yeah, so already I think I have received one answer. All the participants can participate here. I'll wait for some time. So you can rate the webinar on a scale from 0 to 10, and so that we can get some feedback about how you have enjoyed this webinar. And all the participants also can view this feedback. The individual feedbacks are not visible to other participants. So as of now, the average rating is around 9.8. So 19 students, participants have already submitted their feedback. I expect some more. I'll keep it live for some more time. So 26, 27, yeah, it's increasing. Thank you all for the nice rating. So till now, average rating is 9.8. It's quite good. Yeah. So I hope, 49, 50 ratings so far we have received, and we are receiving much more. That's a great thing. It's visible on screen also. I am having a look at YouTube as well. Thank you very much to all the participants. Okay, so till now we have received 92 responses. Okay, 95 responses so far. I'm also adding to the stream. Kallol sir. Yeah. Yeah. Yes,
Yeah.
sir. You are on screen as well. I'll share my screen again, and I'm adding Anirbanda also on screen. Yeah. So you can have a look at the feedback as well. Yeah. Okay. So yeah. So we have already received 112 responses from participants. So average rating is around 9.7 now. So thanks a lot to all the participants. Okay, I'm going to the next question. Yeah, I'm going to the next question now. Okay. Okay, this is the next question. What has been the best in this webinar? Okay, there are several options. What has been the best in this webinar? Okay. So all participants can see this particular question on their mobile screen. Okay, so for this also we have received full screen. Yeah, make it full screen. Okay, so I think it's not displaying the result here. We have received several. Okay, actually it should display the results. Okay, maybe there is some problem. Indeed. Okay. I'm also going to the next question now. Let me see whether it works or not. Yeah, yeah, this is working. So would you like to attend webinars by Department of Mathematics, Gurucharan College in future? So several responses, mostly yes. So thanks to all the participants. Okay. Okay. So several responses, 127 responses so far. It's increasing. So it's very good to see so many participants attending the lecture. (134). So we will be very happy to organize. The Department of Mathematics will be really happy to organize other webinars and any other academic program in near future, and we will definitely let everyone know. So thanks a lot to all the participants. 141 responses so far. Thank you. So I'm hiding the screen now. Okay. So yeah, I have stopped sharing. So I think the feedback was visible. Yeah, Anirban sir, was the feedback visible?
Yes, it was visible.
Okay.
You must be a very happy and satisfied man now.
Yeah, the second question, I think while setting up the thing, I forgot to choose the option for the responses. So that's why probably it was not showing. The results were not showing up. So it's created using mentimeter.com. That's a very good feedback taking website. So live feedback was taken here. So thank you to all the participants. Thank you to all speakers. I'll just post the feedback form here. So once again, I would like to thank Kallol sir and
Thank you.
for being with us. So sir, thank you very much.
Thank you, Anirban. So you
Thank
are
you,
now in Christ, Bangalore, no?
Yes, sir. Yeah.
I'm
Christ.
speaking with the team.
I know someone. She's working graph theory. You know this? Yeah,
Name?
one lady, graph theory from Jadavpur University, basically from Dibrugarh or something, someplace. She did her. I
No,
forget.
no.
Iba Basu.
No, she is not working now, I think.
She's not working now, no? Okay. She was working there.
I believe so, but maybe for a very short span of time.
Okay. Okay.
We
Anyway.
had a conference in June. There are two colleagues from you. They came. Before you,
Okay.
I believe you have conducted one international conference in January or February.
Yeah, January. Yeah, Debashish was there. Yeah.
Yeah, I was there in this conference. So for the participants, I'm sharing the feedback link in the live chat box. I will also share it in the YouTube comment section. So many of you, no, not many of you, some of you could not find the comment section in the YouTube. Actually, what happens? There is a button. Means there are two portions. One is a live chat, and another is the comment section. So when we close this session, you please do not go to the live chat. You close that live chat. There is a cross mark on the top right corner. You can close that, and then the comments section will appear. And on the comment section also there is an option. There are two options: show top comments or show newest comments. So if your YouTube setting is given as show top comments, in that case you may not be able to see the feedback link. It may not appear in your app. So please change that to newest. So all comments will appear. So yesterday in one of the videos, I had to post feedback link more than 10 times. Most probably, yeah, because some of the participants were not being able to see because of that setting in their YouTube app. So this is a reminder for the participants. If you are not being able to find, just carry out those troubleshooting. And even then, if you cannot find, you can always mail me. Not a problem.
Okay,
And for the certificates, yeah, sir.
Okay, Devashish, then I will take.
Yeah. Oh, yes, sorry, sir. I forgot to tell. Yeah,
Everyone, thank you very much. Bye.
Yeah.
Hope to meet you once this COVID era is over.
Sure.
Devashish, thank you so much once again.
Yeah,
okay?
Thank you, sir.
And say hello to Moon also, right? Yeah, from all of us here in Kolkata.
Thank you, sir.
Okay, bye.
Okay,
bye. I'll share the slide in mail to you, right?
Yeah.
Okay, bye.
You can click the Leave Studio option.
Yeah. I'm just leaving. Bye.
Okay, bye. Yeah, Anirban, sir. Yeah.
So do I have to stay back, or I can also?
No, it's okay. You can also leave. I'll just have a chat with our participants.
Okay. Thank you very much, Dr. Devashish, for such a brilliant and commendable job. Thanks.
Bye. Okay, so for the participants, regarding our certificates, we will analyze the feedback links today, and by tomorrow, means only those participants who submit the feedback link will be sent the links for obtaining the certificates, and only those names will be listed who have submitted the feedbacks. So please submit the feedbacks. The links are still active. You can submit. Okay, we will analyze the feedbacks, and we will in the form for the certificates, you cannot fill up your form manually, your name manually. The name will appear in a drop-down list. So that list will be created after analyzing the feedbacks that we have received for the last last 3 days. Okay. So in the meantime, I'm posting this feedback comment again here, so you can just have a look. Okay, and I'll post it in the comment section of the YouTube video also. So there is in my channel you will find a playlist. In the playlist option, when you open YouTube, in the playlist option you will find this international webinar series playlist. So all the videos are available in that playlist, and you can also get the feedback links there. Okay, so thank you very much. Thank you very much for attending this international webinar, and we are very glad that we have received very nice response from all the participants and lots of feedback. Yeah, so there is a question from here. What about certificates of participants? I have already answered. We will provide after analyzing the feedback links. Okay, so please fill up your feedback. If you are not getting your name, you can just mail me. I have checked. Already I have resolved. Yesterday also I had asked many of the participants who could not find their name. So I have already resolved those issues. And even in today's one, if you are not being able to find, so there are some problems which I would like to share. While submitting the registration forms, many of you had written your name as Mr. Yeah, it was asked also that you can provide your title there. So many of you had written it as Mr., Miss, Mrs., Doctor. Okay, so if you are not being able to find in alphabetical order, just have a look at those Mr., Miss, Doctor, Mrs., Professor. Okay, then yeah, then you will be able to find. Still, if you are not getting, you just mail me. I'll just check it out quickly. So there is a question from sir. Please organize on mathematics tools like Scilab. Yeah, definitely we'll think of organizing such a lecture. It will be sort of practical oriented lecture. There is a tool called Scilab also. Sorry. There is a tool software called SageMath also, which is also freely available. And in fact, I am teaching it to my students in college. Okay, so we'll think of organizing such a lecture. Okay. Right. So yeah. So yeah, thank you for all the feedbacks, and yeah. So I hope the seminar is successful. I am closing the broadcast now. Thank you for participating actively. Thanks a lot.